So we thought this is a sexier title. We're going to give a bit of context about our project, which was with Josephine, who's already left, and talking about computer music and data and machine learning a little bit, and evaluation, and some ethical considerations to end with. So DAQRI, Data Science for the Study of Calypso Rhythm Through History, is a project that was funded by a kind of UK-French collaboration. It started 2 years ago, almost, right? And the idea was to bring engineers, musicologists, and composers together to tackle complicated problems. And these are, this is what we said we were going to do, and we did some of it. So the idea was kind of an kind of cross, really interdisciplinary discussions about how the question we are interested in can be rephrased and communicated across the fields. And notice that we are going to focus on the last part, study the concept of musical style through a comparative diachronic analysis of a music corpus, which we maybe did a little bit, and to transform the features extracted from the same corpus into new styles, which we kind of also didn't do, but at least we transposed it into new compositions. And there were kind of interesting challenges that were not quite what we anticipated, but they were fun. Just kind of translating languages between disciplines is, I think, probably a lot of us are doing it. It's very hard to just ask the question in a way that is translatable to the other discipline is very difficult. And it took a lot longer than we hoped. And the kind of posing the questions is the really important part of any of this kind of research. We can each generate answers, but usually the answers we know how to generate are not interesting to our counterparts. So we have to kind of find a way of asking the right questions. And then, the problem of working with field recordings is something that some of you are kind of very familiar with. We had no clue, and we thought we could get some. They had a large collection of calypso music, as Josephine showed yesterday, and we thought, okay, we'll apply mirror techniques, we'll get some information about the style, and then we'll transform it. And of course, you extract features and you extract noise, right? So that was a lot of problems, and we just committed ourselves to saying more in our book chapter. So these are publications that came out so far, and we are focusing on the bottom half. So the two ones there that are don't have anything to do with calypso. So a bit of a step back. Computers are really good at following instructions and really good at handling numerical data. That's trivial. Music can be codified. Music theory is a kind of codification of music with this, and could be digitized. So why don't we combine these two? So we take music, we codify it, we put it into the computers. The computer then spits out music back, and we have a generative system. A brief history lesson. Learning to compose in the style of, so what we call pastiche composition is really the bedrock of teaching music, particularly composition, for centuries. And you learn to do 16th century counterpoint and Bach counterpoint and harmony and all that. That's kind of pastiche composition, learning in the style. Which means we have very good codification of that into a set of rules. This is what you do, this is how you learn this system. And this codification meant that you could be translated into computer code. And if you don't know, this is the first piece, computer-generated piece. Iliac Suite in the that was a mathematician and a composer worked together. They codified the rules of species counterpoint into the computer, and then generated music, and they generated the Iliac suite for string quartet. I notice it has 4 movements that are titled experiment number 1, 2, 3, and 4. They're tackling different questions. And now evaluation of sorts. So the first 2 movements were about species counterpoint. And this is music that it's kind of what you're supposed to learn how to do. And I think we should say that this is, shouldn't be recorded, right? Because I'm going to play music that is copyrighted. Something, it didn't learn species counterpoint, clearly. So there is still work to be done, right? But this is 1957. So since then, there is a lot of applications of computer music to generate pastiche composition. And the question is why? This is maybe a kind of personal take on why. So it's a good teaching computer or codifying computer species counterpoint or harmony into computer code is a good exercise in programming because you know what the rules, it's translatable. Implied in the agenda of getting computers to generate pastiche composition is that by generating correct or solving this problem correct, the computer generates something, learns something about music. And the way I put it is, why do we do it? Because we can, and because the results look like music.
So the approach that we took is not to explicitly specify these rules, but to learn them from a large data set. So this is an example of statistical machine learning. And this is a way to get around the explicit specification of these rules. There are methods to make computers learn patterns from data. The most relevant or the most exciting example today that you hear about in the news is deep learning, and that's an approach that we took in our work. And this, of course, requires a lot of data in order for the system to figure out what are those patterns that, that characterize these styles. The resulting programs must be approached with caution, though. It's not necessarily that they're learning to compose, but they're just merely pattern production tools that are assembling these things that it has no idea what it's going to be used for. It just knows that they're highly likely given the data it has seen before. Examples are, outside of music, what characteristics are associated with a person's defaulting on a loan, what are the objects in this particular image, and can you recommend me some new music? So users of Spotify who use Discovery Weekly get weekly recommendations of new music. But here's an example, an analogy of what statistical machine learning is doing. Consider you want to train a painter in landscape painting. So we take this painter in a variety of landscapes with mountains, with rivers and plains, with different weather conditions, different lighting conditions, and in each location we have that painter paint the scene that they see and then recommends changes or say, well, that color is not correct or that stroke is not correct. And then eventually the painter becomes so adept that they're able to paint in the studio without any landscape. So it's imagining possible landscapes. And then when you look at these landscapes that have been painted without any reflection of a real landscape, you can judge the plausibility of these landscapes. And this is essentially what we've done with our system, but with regards to music transcriptions. So we took a bunch of data. This is a really great repository online, a crowdsourced repository of transcriptions of music typically played in sessions, which happen in pubs and festivals where musicians gather a fiddle and button box and guitar and all these other instruments to play these melodies. And so the transcriptions are available here. You can search for them. There's about 40,000 transcriptions, but after extensive cleaning and removal of a lot of the duplicates, you only have 23,000 plus. So here's an example from the data set. At top is what it appears in the data set for a single tune. You can see the title of the tune and the type of dance it accompanies, the meter, the mode, and then all of these symbols here are specifying pitches and durations and groupings and measures and repetitions. And this notation is called ABC notation, which was developed by an enthusiast of folk music who was traveling around Europe, couldn't read music notation, but needed a way to remember the tunes he was learning, and so would write out some of the first pitches to jog his memory as to how a tune goes. And it's developed into its own use through these groups that communicate this music through ABC. And so at the bottom is common practice notation of the tune at top. So what we want to do is to build a model that will take any beginning sequence. Say you've given the model, you say the beginning of this transcription includes these symbols, and have it predict the next symbol, and then have it predict the next symbol. So it's building up this model that works in a sequential fashion, left to right. And that's not really the way I recommend teaching a human being music, but that's an easy way it's a quite direct way to teach a machine about these sequences. Our code is available. In particular, it uses what's called a long short-term memory network, which is a kind of recurrent structure with neural nets and nonlinearities. And all this code is available online. Our training data is available online as well at the Folk RNN website. So we get to the evaluation. We have built from these 23,000 plus transcriptions some model that's governed by 5 million parameters, numbers, and a sequence of nonlinear transformation of these numbers. Now, inside the system, it has some conception of the music, or of at least this really impoverished representation of the music. So how do you evaluate it? And I'm asking, in a sense, we have reduced these 23,000 transcriptions to an archive that we can tickle and have it generate new tunes in the style that it's learned. So it's a rather lossy archive. It's probably not an archive that you would want to use to study the style, rather than go out and actually see music in the practice. But it is, in a sense, a representation of some of the patterns in the 23,000. How good of a representation is it, and how useful? And this is what we've been focused on. We can look at the descriptive statistics of the output and compare it to the input. So this is just taking the system, having it generate hundreds of thousands of new transcriptions from its distribution that it's learned, and then compare some statistics of those generated transcriptions with the real transcriptions to see how they match up. And in the gray bars are the original transcriptions, and the black bars are the transcriptions that have been generated by the system. And across a variety of meters and modes, we can see agreements with at least the populations of the two. That C major and 4/4 times seem to be quite prevalent in this generated system, but also the number of tokens, the length of a tune seems to follow the same kind of distribution, but in the generated tunes it seems to be quite biased to particular lengths. But this is not music, this is descriptive statistics. It's relatively easy to evaluate a system by comparing statistics, and one may feel confident that they're creating knowledge by producing these numbers that you can test statistically, but it's not actually music. So that's what we move to next, evaluation by music analysis.
So what we did is imagine the system as a composition student that comes to a composition teacher with some of these outputs and say, okay, how is this? So we might do something like this. So here is one example output. And then we can start noticing things that the system did learn something about repetition of patterns, but also variation of patterns. and also that it learned, first of all, it learned that there are two phrases in this style. There are kind of 8 bars and 8 bar phrases. The second phrase is slightly different. It's kind of a higher register than the previous phrase. There are kind of melodic contours that are, again, different between the two phrases. And then there are kind of even some structural tones that the highest note in the first phrase appears only once, and it's kind of in the middle. So all these things are the things that as a composition teacher you might look at when you're talking about melodic, how to write a good melody, or what to think about when you're writing a melody. But another thing is, okay, how about we perform this piece, and we gave it to a musician who specializes in Irish music and performs a lot. And the first thing he did was he kind of looked through, he chose this, by the way, and he made some small changes to make it more playable and more, a better kind of, instead of like a running 88th notes, he's kind of doing some longer notes, and he had the kind of repeat parts so they'll flow back, forward, back and forward. And he these, and then we asked him to bring, and they performed in a concert this tune. Right? So it's actually pretty good.
So that was one tune that the musician selected out of a volume of about 3,000. But of course, there's a notion of cherry picking. How often can you find a good tune among these thousands of tunes that we've generated? So to answer this question of, let's present all these tunes, pimples and all, we generated the Endless Traditional Music Session, which currently has about 47,000 generated tunes. We have not hand-selected them. We've written a simple performance script, which will sort of follow the instrumentation and some of the peculiarities of human performance to try to mimic at least what you might hear these tunes interpreted as. And every 5 minutes, this web page reloads 7 new tunes selected from the 47,000, so you can listen to your heart's content at this playlist. And let's have a listen to the 5 tunes, or some of the tunes that have been selected just now. So in some of these tunes you can see numbers and titles and words. There's actually tunes from 3 different systems. FV3 is the most recent system that's been trained on a reduced, smaller representation of the music. The ones with actual titles, these titles have been generated by the system, and it's proceeding in this character-wise fashion, and the other ones are from a second system. So let's listen to Cluck. I've never heard that one before, but I do like the cluckiness of it. And let's see, FV3. So some are more successful than others. And of course, there are failures in there. So here's some examples of failures. One example here. And then here's one that the system is titled Chicken. So these tunes, or especially the last one, you would never hear at a session. But what's interesting is this system is relatively consistent with these notes that are in the curly braces, which are grace notes. And its use in these, across all of these phrases, sort of signify it's a pipe tune. It's imitating some of these pipe tunes that are in the collection. So, of course, this website allows us to evaluate the output of the system by the wild World Wide Web. We've produced 14 volumes of session books, and this is 40,000 transcriptions and staff notation in ABC. And we took this back to the session website and said, here's some examples on the Enlist session. Here's some examples that are printed in these books. What do you think? And so some people were not very impressed. A computer that noodles, that's all we need. These are terrible. It's crude turntabling. You need to teach it to dance first. And I think that was the most poignant and most relevant criticism of this system, is that training it on the transcriptions misses the point of the music and the practice. This is meant to accompany dance. And how you perform these transcriptions is how the dance is performed, where the emphasis is. All of this is missed through the transcriptions. Another person was very adamant that, very against it. It's reckless to send thousands of machine-created fiddle tunes into the world. This person was very concerned that our 14 volumes are going to be misunderstood as a reflection of his tradition that he loves and he sees as a gatekeeper of one. All right, so presenting these tunes in transcription formats and as syntheses is one thing, but what about performing them, recording myself performing them online and posting that? So the Trunk and Pint was one tune that I posted. I got 445 views so far. I've got 5 thumbs up and 1 thumb down. So this experience has hardened me as reflect on the criticism, but all right. And then evaluation by experts. So I'm not particularly an expert in this Irish music. I love playing on the accordion, but let's get some experts in there. And so we have 2, we've worked with several experts, but Darren and Una are 2 that are devoted to this tradition. Una in particular has grown up in the competition type of competition in Irish music and traditional music, and she has a very different perspective than Darren. Darren was surprised at how good the fake tunes can be, and he estimated, while looking through these 3,000 tunes in one volume, that about 3 are okay and 1 in 5 are pretty good. But he had little trouble in finding material to work with, actually. So that was a good sign. Una has said that this raises questions about the very nature of folk music. And you're playing it and it feels familiar, but it doesn't. She also mentioned that when she was practicing some of these tunes, it felt like measures were taken out of context from other tunes, existing tunes, and mishmashing them together didn't really make sense. She's not sure how excited she'd be to perform them because they mostly sound like mixed up tunes. But we did convince her to take some of the tunes and compose a piece with them and perform them in public, which will be, the recording will be available online.
Okay, so our aim is not to overtake the tradition, but can this be used as a composition assistant in some way? And I'm a composer. I'm interested in trying new things. So I thought, okay, I'll write my folk song arrangements, except that fitting the 21st century, the folk songs will come out of the system. Turns out it's more, or it didn't turn out quite the way I thought. So my idea was, okay, as I said, it learned about transforming and repetition and variation and stuff. So I'll just plug my music in, and it will give me tunes that have transformation and stuff. No, it doesn't work. If I plug things that are really not very Irish, it kind of loses its sense. So in this case, I gave it something that's not quite Irish, and it just ignores whatever I put in. It just does what it always does. Sometimes it kind of takes on board some of it, but it becomes still quite weird. And when you try to put these dyads, it solves so very little of them that it kind of becomes even more awkward and loses its ability to count. You see that measure 12 also only has 3/4 when it should be in measure 7. So it really goes haywire when you're trying to really force it away. So I needed to kind of step back and say, okay, how do I really do it? How do I compose with this as a system? So that came Bastard Tunes. That's hopefully some of you heard on Friday. We do have some parameters to work with the system and not just generate tunes. How much do we have still?
We started 5 minutes late.
We started a bit late, so hopefully we'll be on time. Yeah. So we have a temperature parameter. So the system learns a distribution of what is the likely next symbol. And you can set the temperature, so if it's a low temperature, it will pick the kind of most likely event. If it's high temperature, it will more pick from the kind of edges of the distribution. So you can kind of tune how conservative or adventurous it is. And so, for example, for my first movement, I started it at very, very low temperature, four lines going in parallel. So at very low temperature, it kind of sticks almost the same. All four versions will be almost the same thing. So I get tunes that are only kind of a few notes depart. And then as we go along, it kind of becomes more and more separate, but it still keeps the rhythm together. And then it sometimes generates a new pattern, and I gradually increase the temperature. So I kind of generate 16 bars, which is more or less what it generates. I take the last bar, put it back into the system, and then regenerate with a slightly higher temperature, and then take the last bar and put it in, generate with slightly higher temperature, and kind of went like this like 10 or 15 times and got a pretty long thing. And you hear that it kind of does. Right, so they're kind of together, but they're gradually drifting apart. It took 2 iterations to get it to drift apart. For another movement, the third movement, I took a kind of different approach. I generated a melodic line. I wanted a slow movement, and it's hard to get this piece to generate slow music because almost all the tunes are pretty fast. But eventually, after a lot of trials and tweaking, I got it. And then, so I had, at the bottom, you see that's the actual tune I got out of it. It miscounted some stuff, so I had to fix it. And then I treated fairly freely. I kind of adjusted the rhythm. If I needed another bar, I added a bar. If I didn't like a bar, I deleted a bar. I found, essentially, I found interesting material in the tune and then made it a bit more interesting and distributed in interesting ways to the ensemble. And so that's the process that I took.
One thing we didn't anticipate here were ethical considerations. When we started to present the stuff on the web back to the practitioners of this kind of music, or some of them, some of the responses, offensive responses, gave us pause. So what rights do we have to this data that have been collected by this group of people? And are we using it in a way that the collectors did not anticipate? Are we being unfairly rewarded with grants and publications and media attention and invitations to symposia to present this work? Right? How can we pay back to the community? Who owns the output generated by the system? Is this going to lead to replacing humans, which the media loves to push? And will this devalue the music? Are we trivializing a tradition? Right? So this is Michael Flaherty, Lord of the Dance, and we want to avoid being the Michael Flaherty. And of course, the tradition of Irish music, it's a living tradition now. This is different from a waltz tradition. And so the Schlagermusik with André Rieu is a different kind of trivialization. It may be a little more accepted than Michael Flaherty. So future directions with this work. We want to make the folk RNN models more user-friendly. So we're developing a system that we can put online for anyone to interact with. And next year, we're going to hold a composition competition for works that are created using our tool. We're going to link to another website that is depositing and commenting on tunes that are generated by the system, and safeguarding the machine folk community, which is a new genre that I'm pushing. The current membership is 1. And working with polyphony as well, and non-Western traditions. This is a great project for any student who's looking for some undergraduate project or master's project. And then other generation models that go not left to right, but may consider the endpoints that's needed or go right to left. There's a whole variety of things. So in conclusion, we've applied the state-of-the-art machine learning to 23,000 transcriptions of traditional music using these models, and we're evaluating them in several different ways. None of these ways involve this toy Turing test, which is the real tune, because we find that question to be absolutely irrelevant to what we're trying to do. We're not trying to fool humans. And we've collaborated with composers and improvisers to see how this can be integrated into the practice. Does it bring anything into the practice? How can we improve the models that we built? Works that have been created with the system have appeared in 5 concerts so far, and our main research questions are about co-creation and how, back to the daiquiri project, how can this practice inform machine learning and data science and vice versa. So some basic acknowledgements. Thank you very much to the organizers of this conference and to Volkswagen for facilitating the conference, a developer of the session.org, as well as its many contributors, and many of the musicians we worked with. So you can Google search Folk RNN. We have dozens of compositions and recordings of this music online that you can find, and we're happy to take your questions.